Hi guys, today I'm gonna have a review of the paper Listen, Attend, Spell and Adapt Speaker Adapted Sequence-to-Sequence ASR by Dr. Felix Winiger and his colleagues. Before I start, let's take a look at the key concept mentioned in the paper. It's called Kullback-Leibler Divergence, or in short, it's called KLD. What's that? Well, this concept is trying to measure the distance or the similarity between two probability distributions. Say I have a random variable x. In certain case, the probability distribution of it is called p of x. And there's another probability distribution, let's call it q of x. Okay, so let's ask the question, what's the distance between p of x and the q of x? So in the KLD definition, the distance is not a symmetric distance. Suppose I want to get the distance from Q to P this way, okay, this way. I would use this equation to calculate the distance. So it's the integral over x, and the function to be integrated is px times log px over qx, I think. px. Okay. And of course, you can see this can be also written in the form of expectation. Okay. Expectation of log p of x given q of x, right? But this has to be under the p, right? So I won't have time to go into why and how this KLD got developed, but all you have to remember is that first of all, suppose p of x is the equivalent of a q of x at given any x. This dp from q to p equals to 0, right? And the second thing is that dp to q to p does not always equal to the KLD from q p to q. Okay, and this is why, because the second probability this feature, and sometimes in some cases we do need symmetric distance, so people develop the KLD2, and in this case the distance between p and q equals to dp q to p plus the dp to q. Okay, so this is symmetric. Yeah. And also the KLD has another name, I think it's called the relative entropy. Yeah, it makes sense because it's always have the notion of comparative or related. So if you say the entropy of the P is always given the P and Q, right, with regard to the certain distributions. Okay, So how the KLD is being used in the speaker adaptation. I will give a very quick overview of what is speaker adaptation. Okay, speaker adaptation. Well, suppose I have a Google Home, right? Remember when you buy this Google Home, this Google Home will ask you to say, "Okay, Google," right? My cell phone triggered it. Oh, I know. Okay, got it. Okay. Ask you to say this several times. This is what I guess what Google is doing here is trying to adapt certain part of its speech recognition model according to your voice features or voice characteristics. Why do they have to do this? Because two reasons. The main reason is accent. So although the speech recognition, especially for general American accent speech recognition, is doing very well, but within America there are more than at least 5 to 8 general region of dialects, not dialects, accents, and also children, seniors, adults. They all have different type of a voice, vocal tract characteristics. This contributes to the difficulty of speech recognition, and then this is why the models being used in the speech recognition is better to be adapted or adjusted. Or I think nowadays in the machine learning people call this fine-tune, but in speech people prefer to call adaptation. And the speaker adaptation is just one aspect of the thing that has to be adapted. The other part is the channel, right? What do I mean by channel? It means suppose I'm in this living room and talking to you, or suppose I'm on the telephone channel and talking to you, and suppose I'm in a subway which is very noisy. I'm being recorded. So those are different channels, and most of the time the speech recognition works very well under the clean condition, which means in the studio room, no noise is presented, you have the closed-talking microphone. But most of the time, like the cases I mentioned, the recognition accuracy will degrade, right? This is why you have to also adjust your model, or you say fine-tune your model. Speech people call that, we do adaptation. Adapt the model to get better recognition accuracy. Okay. Then let's move on to the paper after I explain the basics to you. I do recommend everyone who is interested in the speaker adaptation to pay close attention to this paper. I think this paper has been written very clearly compared to other papers. Its introduction, I will skip it. It gives you all the reference that you need, very good references. Okay, talking about the method. First of all, they use the architecture called the LAS. For those of you who are not familiar with this listen, attend, spell architecture, check check this keyword, listen, attend, and spell keyword. Just search this in the OLED web channel. Okay, I have an overview of this one. skip this part, and the KLD adaptation. Okay, let's say the equation 7. This is a key part of this paper. Okay. Let's see the first part, the cross-entropy part. I think this is easy to be understood by almost everyone who are familiar with the general machine learning. You may ask, what is y, what is p, pi? And you can see in this figure, the y star means the transcription, okay, or labeled speech, labels the content of the speech that is being labeled, that has been labeled, and the pi means the prediction, okay. This is easy to understand, right? The KLD or KLD related term is on the second term. Okay. And remember, like I mentioned, this, I think the author actually meant this is the summarization of all the samples. And this is the PI, I think the PSI, right? Yeah, correct me if I were wrong, comment on my YouTube channel. Okay, so this is, I decompose or written this KLD term in details, okay? And then you may ask, so what is, I understand what is PI, but what is PSI and PI, okay? Let me introduce you to the stuff over here. What does the SI mean? This means the speaker independent. Okay, which means it's a general speech model. It regardless which speaker is talking to it, it will treat all the speakers as just the one speaker, or nobody has difference. And you can see this type of, I think it was back in 2019, no transformer has been introduced into the speech yet. So this is why you see the author is still using this bidirectional LSTM architecture as the encoder, and this is a decoder. But it doesn't matter. It doesn't affect the underlying architecture of the model. So you can see the input, the raw feature, get input, and after decoder you got the output PISI, okay. PSI of I. I is the ICE output textual label, okay. And the same thing happened here. Let's do not look at the U and the U prime stuff. And all you have to see is this is a SA model on your right, okay. What does the SA model mean? Yeah, I guess you all have guessed, right? This is called a speaker adapted model. Adapted. But I think it's better to be called, or you can see this in other paper, it's called a speaker, sometimes called speaker SD model. I think it will be more common to call that speaker dependent model. Dependent model, okay. And you can see the same input I got input there, but at output, you can see this is a PI. What does it mean? That means the speaker label has been taken into consideration. So unlike the NLP task, when you train your encoder or your fine-tune your task, there's no speaker label there. But in speech training data, many times you will see, suppose I have a sentence 1, sentence 2. I will use S to represent sentence, okay? Sentence 3. And during recording, most time the data collector will label this. All these 3 sentences are coming or recorded from speaker A, okay? And then you can see 4 as 5, these 2 coming from speaker B. I hate my writing. Okay. So you can see it has this information here. Then in training, what they can do is that, suppose I know this is speaker A, okay? When I am using speaker A to train, I can do this. Suppose I already got a SI model and I want to adapt, or in a word, fine-tune, okay? Fine-tune this to a speaker adapted model of speaker A. So what I do, so I only use the S sentence 1, 2, 3, not S4 and S5. Just only these 3 sentences to send into the network and get the output and use the backprop to update the primaries. But you say, wait, this can be overfitted, okay? You only have 3 sentences. I just use this example. And in this paper, I think the author said they have 20 hours of each speaker's data. I think that's pretty much enough for you to have a good fine-tuning data. And then in this case, actually the PI is meaning that you have the softmax output of a specific speaker. Just one speaker, okay? One speaker. And then the PISI means that when you're using the same input, but you do not do any speaker adaptation, you got the original neural network, you got a softmax that is not changed, okay? And then they use compare, because softmax are all posterior probabilities, or they all can be summed to 1. So you can plug that into the KLD framework, right? Okay. So this is why you can calculate the KL divergence for this sentence. And after you're done with this sentence, you sum over all the samples, then you got a sum the KL divergence. I think I might have made a mistake here. This means all samples, okay? I think some of you may have noticed that I missed another summation over here. Okay, so the I equals from 1 to C. What does the C mean? C is the number of classes. Okay. The number of classes. And then after you do this, this is the KLD for one input or one pair of input and output. Then you sum over all the samples, or the sentence of speaker A, okay, or the sentences of speaker A. And then after this, you sum over all the speakers. Okay, so then you can see that you get all the everything here, and this one I don't have to explain. And in the end, they use a weighted sum, right? Okay, here's the equation, but but people may ask me, okay, wait, what's the point having this extra term? Because for me or for them or somebody, I think this one is enough for me to run fine tune. I think you're right. Most time for the fine tune, people just use a lot of data to just update the cross entropy, right? Trying to minimize this. But what does this term stand for? Okay. Let me tell you something. Remember, sometimes when you do fine tune, you want to do something called a regularization term. And why do you need to do regularization? You want this to prevent your model from overfitting, right? So actually, the KL divergence term is the regularization term in this speaker adaptation or fine-tuning. And you can see that because sometimes the number of sentences are not that large enough, and then if you just do this, your model could be overfitted. But once you have this, what does this mean? Because you want this to be as small as possible, to be closer to 0, right? Remember I mentioned that when these two probabilities are exactly equal to each other, guess what will happen? This loss term gets to 0, right? And this is the purpose of having this regularization term. Because this one is fixed, right? Fixed. And then you update your model to get this PI changed. Okay. And then when you want this to be as close to 0 as possible, then you want to say this. I want the difference of the probability distribution of PI to PSI is as small as possible. So you want these two distributions to be close. So, or in other words, you do not want the model you adapted to be too different from the original model, the regularization term. Okay. After we figure out this, let's look at into the details of the network. So you can see in the SA model, during the decoder, they have some extra U over there, right? And after, before they output the contextual vector, they have the U prime, this stuff. And at the decoder side, they have this type of U prime, the decoder. These are the encoder. Oh, you may not be able to see this. Let me draw this here. Okay. Decoder. This is encoder. So you may ask, what is this? Why do you have to do this? This is called LIN. So I think this traces back to the adaptation in the acoustic modeling, but I don't want to cover that today. It's called a linear input network, I think. And this one is a linear input network. And they have LON. It's called linear output network. These are the LONs. It's because the author has tried that, okay, and he said the KLD has to be used together with the LIN and LON. I don't have much comment on that. All he was saying is that you need to have some extra layer at the bottom and at the top. He did some minimum word error laws. I think that's new in this paper, so I will skip this. And the LM fusion, the decoding, that's not new. For the experiment, I say that the result is really good, and the description of the experimental setting is very clear, very clear. Yeah, I think I want to get this. I think he actually means it LHN. But I think those are the namings. They don't make much difference to me. The H stands for hidden. Okay. Yeah, I think those are hidden layers or. Okay. There is a very interesting result showing in the figure number 2. And what it is demonstrating here is that first of all, the baseline KLD, he just used the stuff he was working on is end-to-end speaker adaptation. But what he meant the baseline KLD is that he used the hybrid model, the acoustic model plus language model, okay, the HMM stuff, and there's no there's a KL. For the hybrid model, you can still do KLD, but it's only on an acoustic model. Acoustic model is neural network. You can do the same thing as he described in the end-to-end. This one, you can see that the interesting thing is that the baseline is better than the sequence-to-sequence model. You can see that, okay? And you can see after you have more than 2 hours of adaptation data for each speaker, the reduction of WER start to getting smaller, okay? It will not change too much after 8.5, right? And he's saying that suppose I use the LHN when there's no KLD, I think just the KHN, this one, just the LHN, no KLD. He said this is not very working much, okay? It's only get about 9.5 and it start to plateau also around 2 hours, not working. But once he add the KLD in the loss, also together with the LIN and LON, okay, what he was observing was that the more data you have for adaptation, the more job you will get, and it's a linear. It's linear. It's very beautiful. Very beautiful, and eventually it got lower than 8% in WER, which is better than the baseline. It's very good results. Consider that he's publishing the paper back in 2019, not today. Very good results. But I didn't see him talking too much about the reason why KLD is better than LHN and why eventually end-to-end speaker adaptation outperformed the hybrid model. I didn't see that, but it's experimental research, so he just put the results there and let other people think what is happening there, and it's good enough. Finally, in conclusion, I think what he was doing that is saying that some future work. I like that. Not a lot of people are mentioning future work in their conclusion. First of all, they will try to see something they can do in the language model, whether they can interpolate the general language model and the speaker specific language model. For example, like me, I like to say filler words more often than lots of people, like but something like this. If you can adapt the language model according to my spoken behavior, you might get better recognition accuracy. And the second thing he wants to do, I think he's more excited about this one, is that he wants to explore a vector for end-to-end based speech recognition. I think that's also a new topic, interesting. All right. If there's no question, I will stop here. Thanks for watching. Please subscribe to our channel. Goodbye.